At the dawn of the space age, there was little consideration of how to properly archive data collected from missions. As a result, much of the early data was poorly documented and stored without any standard practices. In this video, we will describe the key challenges and considerations involved in restoring this vital early data. The NSSDCA serves as the long-term archive or vault for planetary and space science mission data. We've been preserving data from all the way back to the 1950s from missions like Explorer 1 and Apollo. In fact, some of this legacy data exists nowhere else. This data is a unique and valuable resource that can help scientists study how space and planetary environments change over decades and thereby give us insight into long-term trends and rare events. There are many challenges when dealing with legacy data. First, what is legacy data? It is data stored in an outdated format, making it hard to access with current computer technology. Archiving as a practice wasn't generally considered until the 1980s, and early data were frequently not properly documented. The restoration of this data is important not just for the permanent archive, but also for future accessibility. Most planetary missions and their data are sparse. They happen once in a decade and are limited in time. Data related to a specific discipline or application can be especially low in abundance. Therefore, existing legacy mission data is of great value, and we still receive requests for this data from scientists, particularly those who want to prepare for new missions and/or verify or enhance new scientific discoveries. The 1990s brought in the era of data standardization. Prior to then, datasets were written in formats specific to legacy hardware like IBM, VAX, and UNIVAC, which creates a major compatibility issue with computers of today. The NSSDCA handles differences in data encoding, Indianness, and even numeric representation methods like 1 or 2's complement. In each case, each dataset presents a unique technical puzzle. For example, each character or byte was written initially in BCD, or binary coded decimal, which was used in applications where decimal fraction precision was critical starting in the 1950s. Unisys field data, used by the UNIVAC 1100 series starting in 1962, EBCDIC, or Extended Binary Coded Decimal Interchange Code, which was devised by IBM in 1963 and used in their mainframes, and then finally ASCII, or American Standard Code for Information Interchange, which was first published by IBM in 1963. ASCII was mandated in 1968 by President Lyndon B. Johnson as the standard for all U.S. federal government computers. NSSDCA has dealt with at least 4 different variations of BCD character sets. Many of them were written in 6-bit byte code rather than today's 8-bit byte standard. For integers, one of the great debates in the early days of digital computing was the format of negative integer numbers. Some used 1 bit for the sign and the rest for the magnitude, but the addition of 1's and 2's complement made the mathematical operation on binary numbers a lot easier, and eventually 2's complement prevailed. In 1's complement, all the bits, or binary digits, are flipped, so 0 became 1 and 1 became 0, thus indicating a negative number. In 2's complement, after flipping the bit, 1 is added to the result to indicate a negative number. Within each system, the representation used to store the data will end up getting a totally different number as a result. Therefore, it's important to know which system has been used in order to begin the process of reading the data. For floating point numbers, computers represent them using a sign, a fraction, also known as a mantissa, and a base with an exponent and bias. In the past, different systems implemented this differently. For example, some IBM series used 36 bits for single precision, while the VAX 11 used 32 bits. However, the bit allocation for each part varied significantly. For reference, the IEEE 754 single precision floating point standard format is shown on the right. Because of these variations, one must carefully interpret each byte or word depending on the system in which the data was originally recorded or later copied during restoration. Here are some additional challenges commonly encountered when working with legacy data sets. It was common for many computers built in 1960s to have 6-bit bytes, where today the standard is 8-bit bytes. For data stored on a 7-track tape, if we exclude the parity bit, the effective unit was also equivalent to a 6-bit byte. Therefore, word sizes were typically multiples of 6 bits. After about 1975, the standard shifted to 8-bit bytes, but for some time both 6-bit and 8-bit formats coexisted. Data originally written in a 6-bit byte system was eventually transferred to an 8-bit byte system, but there wasn't a single standard method for conversion. One common approach, called zero padding or zero filling, simply adds 2 0 bits to each 6-bit unit to create an 8-bit byte. Another method of converting 6-bit data into 8-bit format is to use the least common multiple of 6 and 8, which is 24. In this approach, 4 6-bit bytes are combined to form 24 bits, and then that sequence is split into 3 8-bit bytes. The challenge, however, is that most datasets don't indicate which conversion method was used, so often the only way to determine it is by carefully examining the data. Here's an example from the Apollo 17 Lunar Surface Profiling Experiment, or LSPE. The excerpt shown here comes from a table that describes the data format. As you can see, the presentation is not very clear, which highlights the documentation challenges mentioned earlier. This table specifies that the data is stored in 36-bit words. Since 36 is not a multiple of the standard 8-bit byte, this strongly suggests that the data was originally recorded on a 6-bit byte machine. When migrating data like this to modern systems, there are usually two common approaches. Each 6-bit unit can be zero-padded to fill into an 8-bit byte, or multiple 6-bit units can be packed together into 8-bit bytes. Another complication in the Apollo 17 LSPE dataset is how the time information is recorded. Initially, the time information recorded in milliseconds is stored in 36-bit words with the most significant bit on the left. However, at a later point in the dataset, the format abruptly changes and the data begins to appear in reverse order. This reversal may have been a hardware-specific optimization used during the mission. The issue became apparent because the decoded values were nonsensical, and a faint annotation highlighted in yellow hinted the reversal. To interpret the data correctly, it is necessary not only to reverse the order of the bytes, but also to reverse the bit sequence within each byte. Another challenge when restoring old datasets arises from Indianness, which refers to the direction of reading and writing the data. Some systems write left to right, and others right to left. If the system stores big end first, or most significant bytes first, it's called big Indian. The opposite is called little Indian. Here is an example of how this issue can affect the restoration of old data. Suppose we want to write the 4-character word Unix, U-N-I-X. On a big Indian system, the characters are stored in memory in the same order as written, with addresses increasing from left to right. On a little Indian system, however, the last byte is written first, so the order appears reversed. Things get even more complicated when the system writes 2 bytes at a time. In that case, Unix, or UNIX, could end up being interpreted as Nuxi, or NUXI, instead. Today we use standardized formats for data exchange, so we rarely encounter this problem. But when legacy data was migrated between systems without proper handling, the values could become completely scrambled. Quite often, we notice that an extra few bytes of header are added to the data files. For example, here is a hex view of a file from the Pioneer Venus Plasma dataset. Each 2-digit hex value represents 1 byte. In this file, the first 4 bytes in ASCII string indicate 0114, which represents the size of one record. However, in this case, the 114-byte record size includes the 4-byte header, so the actual data portion of the record is 110 bytes. In another example, if you read the first 2 bytes as an integer, the value comes out to 1800. This also represents the size of one record, but here the actual data is 1800 bytes, excluding the 2-byte header. From these examples, we can see 2 different ways that headers can indicate record size. One includes the header and the other excludes it. In one case, the size is stored as a 4-byte character string. In the other, it is stored as a 2-byte integer. Are these headers always present? No, they appear to be random. This header information was likely added when the data was migrated from one system to another. To translate this data and make it usable with modern computing systems, NSSDCA is working at the bit level, breaking down bytes into individual bits, rearranging them, and reconstructing numbers or characters from specific bit arrays. There is no simple and standard way to decipher the data. Each legacy dataset comes with its own unique format and therefore requires a customized approach for interpretation and processing. Once restored, we format and archive them using modern standardized formats to ensure accessibility for future researchers. We prioritize our efforts based on community need and mission relevance, whether it's supporting an active user request or a new mission like Artemis or the upcoming Venus explorations. Work done at the NSSDCA is bringing together decades of planetary mission data for today's science and tomorrow's discovery.